Okay, hi everybody. I was getting some strange messages about the problems with the server. Anyway, is everybody there? You can all hear me?
Good, really.
Okay, so what I want to do today is just do one very kind of quick thing, which is just kind of a almost kind of a footnote to what I was talking about before about the about semi-direct products. So what we did last time was that the well, what I'll do is I'll quickly say something about what we did last time and then go over this. But then the main thing that I want to talk about today is actually kind of a very standard topic that's in pretty much all the physics books, which is about the story of the Coulomb potential. And if you have a single particle which is in a Coulomb potential, how do you find its its energy eigenfunctions and its energy eigenstates? So one piece of advice about today is, so the details of this are mostly pretty much worked out in my book, but a lot of it is very much the same stuff that's worked out in I think essentially every other physics textbook. So some of what I'll be saying, yeah, I really recommend if you haven't kind of seen a standard physics textbook version of it, you should go look that up. I will end up doing something which is kind of a somewhat tricky way of using group theory and representation theory to compute in a kind of a slick way the energy eigenstates of the Coulomb potential. So we'll do one thing which it's in a few of the physics textbooks, but it's not in most of them, using more group theory. But most of what I'll be saying today is pretty much a very standard story. But before we get to that, I wanted to tell you a little bit about this, just to kind of review what I told you about representations of semi-direct products, and say just kind of one last thing about them before I move on to something much more concrete. So the story I was telling you before. So the general question is that if you have a semi-direct product and of two things. So this is two Lie groups where this guy acts on this guy by automorphisms. Then what can you say about the representations of these things? And the one kind of fact that you have going for you, so is this that if you're given a representation of n, so there's this map phi, which for each k maps n to itself, preserving the in a one-to-one way, preserving the group law. And so for any let's say it this way. So if you're given a representation pi of n, then this for each k, the fact that phi there's a phi sub k acting on n, and what you can do is you can use that you get a representative, then for each k, small k, and k, you get another called pi sub k, where pi sub k is the thing which it's the linear operator that at n is given by what is it, by pi sub k, pi of, you let the automorphism work on n. Okay, so you take your original pi, but instead of applying it to n, you do the automorphism first, and then you apply. And then you can check that the fact that this is an automorphism means that this is a homomorphism. And so you have another representation. And what we've seen last time, we talked about n commutative. And what's happening is that then the irreps are one-dimensional, 1D, and the set of all the irreducible representations are what I call alpha are and then are, well, I just call it n star. They're also called characters. So the characters of a commutative group are really the set of irreducible one-dimensional representations. They're all. And now what happens if you so if you put this commutative n into a semi-direct product, then what's going to happen is that the group K, for each element of K in K, if you start with one irreducible representation alpha, you get another one. So K acts on n. Taking so in this language, taking alpha sub K, where it's just the alpha is a function, and it's the function that you take the function on n by first applying this automorphism. And so this moves you around the irreducible representations, and we saw, so for instance, in the case of the Euclidean group, you found that this was also just the set RD, and you're just moving around the vectors with the same radius in here as when K using K. That's what's happening in here. So that was the story last time, and I won't go over it again. But there is kind of a general theorem which I didn't prove, but there's a very general story that if you want to know the what all the irreducible representations are in this case within commutative, what you have to do is just look at this space, look at how K acts on it this way, and then look at, and if you pick any particular point, you get an orbit, and you also get a subgroup K sub alpha of K, the stabilizer group, which is what leaves this alone, and then any kind of irreducible representations are then get associated one-to-one with irreducible representations of the stabilizer group and orbits. So anyway, that's the general story, which I tried to tell you last time. So you can kind of completely say what's going to happen when n is commutative. Now, if n is not commutative, there's very little you can. There are things you can say in general, but it gets a lot tougher. But there's one other example which I want to talk about, which is this example that we've been developing, where where n is the Heisenberg group and K is the symplectic group. Okay. And then the symplectic group acts as automorphisms on the Heisenberg group. Now the problem with this is that this guy is not commutative, so this doesn't fit into this thing. But there is something that kind of makes something. There's something interesting that you can say here, whereas normally it's hard to say anything. But here there's something interesting which you can say, which is that in this case you had so here. And here you had an infinite number of 1D ERFs, okay, given by any point in a set. Actually, what you have in this case is kind of the opposite. So here you have an infinite of the Heisenberg group, and unique by Stone von Neumann. So these commutative groups are, they've got this infinite number of very simple representations, simple one-dimensional representations. This group is kind of at an opposite extreme. It's got there's really only one. I mean, again, up to this business about the center, there's really only one interesting infinite dimensional representation of this guy. there's only one interesting one, but instead of being one-dimensional, he's infinite dimensional. So he's actually very hard to understand. You've got one guy, but who's very hard to understand. And here you have an infinite number of things that are easy to understand. Okay, so the kind of footnote I wanted to say today was, I can't use this to kind of classify all the representations of this group or anything, but you can. There is something interesting you can say about what the structure gives you, which I'll say right down here. And maybe just to say before I kind of get into this, maybe there's give you the motivation for why I want to kind of to say this. I mean, it's kind of it's an interesting piece of general theory, but the what we actually have here is this infinite dimensional representation of this guy, we actually have a fairly concrete version of. This is really just exactly our single particle, our state space for a single particle in d dimensions. Remember, this is exactly what I'm calling a Schrodinger representation. We know it's given by just functions on Rd with derivatives and multiplication acting on them. So we have this guy we actually know a lot about. The thing which is actually more mysterious is how this guy, which we know, how he extends to this guy. And so what I'm going to get out of this is one kind of extra piece of information about how this so-called Schrodinger representation, which we already know about, how he behaves under the action of this guy. And what we've done so far with this is here at the Lie algebra level, this was given by linear polynomials, this was given by quadratic polynomials. And so at the Lie algebra level, I could show that I could get a map from the quadratic polynomials to Q and P operators, so that you got a nice Lie algebra representation of this thing. But there's a subtlety which we're going to see a lot when we start doing the harmonic oscillator, which is that the representation you get of this guy, if you try and exponentiate those operators, is double valued. It's very much like the spin story. That you get a representation that's only that's only a true representation up to a sign. And so you can see that same problem here in this general theory, and that's just kind of the footnote I wanted to say today. And so it's this. So here's the one extra piece of information you get out of this. So what you get here is you have so in this case you have it, which I've always been calling gamma S, the Schrodinger representation of the Heisenberg group. And so this is the thing I've been talking about. It's the representation on functions and d dimensions. And then what happens is that you can so SP2D R acts on this, as I was saying, by automorphisms, that the symplectic group acts on automorphism on the Heisenberg group, so it's going to act on this guy. So this so it takes gamma S to something I'll call gamma S, comma K, and this is equal to so this is gamma S, but with this automorphism coming from K applied to whatever your element of the Heisenberg group is. And then, but so it's very hard to kind of to work with this and say what it is. But what you know is that this is okay. So that this is going to be another irreducible representation. But Stone-Neumann says that there really is going to only be. Well, you can also show that this preserves the central element. So with the central element preserved, there's really, Stone von Neumann says that this guy is not something completely different than this guy. He's unitarily equivalent to this guy. So there's some unitary change of basis which makes these two things equal. So there's some UK gamma S UK minus 1 for some unitary operator U sub k. Okay? So this is by Stone von Neumann. But the problem with this is this information. So the problem is it's actually very hard to actually get your hands on U sub k to really explicitly like compute what U sub k is. But there's one interesting thing you can say about these U sub k's is that you can see that so that if you can show that if this is going to be, if this property is going to be true for any k, then if you take two different k's, you find that U sub, so look at U k1 k2. What happens if you multiply two k's? And what you find is that it's equal to U k1 U k2. I mean, clearly, if this is true, then it's going to preserve this property. So you're going to get a nice, your unitary operators are going to be nice. But the problem is that
so you are saying those UKs are not just unitary but also symplectic?
This is what I want. This is what I want to show. So if you have these, you can do this, but and get a representation. But the problem is that these UKs are not uniquely defined. This condition doesn't really tell you quite what UK is, and by Schur's lemma. So UK only defined up to a scalar. Okay, so you've got these. You've got these operators which commute with with an irreducible representation operator, and the problem is that you always that condition by Schur's lemma means that anyway Schur's lemma implies that you're going to have you can only define these things up to a scalar. So what you actually have is if you multiply these guys, there's some kind of scalar e to the I, and the scalar has to be pure imaginary because they are unitary for some of K1, K2. Okay, so you don't actually get a true representation. You get a representation up to a phase, and the problem is that there's really this construction isn't actually giving you what you'd like. It's not actually giving you representation operators for. And if you actually had this, yes, this U sub k would be a representation of the symplectic group. That would be so. This is the condition for these to be a representation of the symplectic group. So what this is saying is that you come close. This construction comes close to giving you a representation of the symplectic group, and it's going to be it's going to be on the same space here. But it only kind of is going to work. It doesn't quite work. It works up to a phase. Okay, and then this in some sense is the same problem I was trying to tell you about before. There's a problem that you can't everything is going to anyway. There's a problem that you can't actually exponentiate the Lie algebra representation to a true group representation of SP. Now, what actually, so this is kind of where I unfortunately kind of have to stop. There's an interesting story. You can then study the behavior of this phi, and you can show that that in this case, for a finite dimensional symplectic group like sp2d, you can show that this phase actually is always going to be plus or minus 1. That, this is some number of pi's, and depending whether it's odd or even, it's going to be plus or minus 1. So you can show, and this is a bit hard, but you can show that the that UK1 K2 is equal to UK1 UK2 times a plus or up to a sign. And so this is something. It's very, very similar to the spin story, and later we'll understand this analogy a bit better. But that the spin, that you have a representation of SP, but only up to a sign. And so if you really want a true representation, you have to go to a double cover of the symplectic group. And it turns out if you go to infinite dimensions, if you look at if you take D to infinite dimension to be something to be infinite dimensions, you look at a Heisenberg group for an infinite dimensional space, then it turns out you under certain conditions, this is still true, but this is no longer just a sign. This is now a function. It can be an arbitrary real number, and you end up with a you end up with a new phenomenon, and that's the phenomenon I'll try to talk a little bit about next semester about. The physicists call the anomaly. And so this is kind of the one reason for doing this is to kind of explain where this if you hear about people talking about an anomaly in a quantization, it's because it's the problem that this guy cannot you can't actually choose this guy to make him go away the way you want it to. Okay, I think I better, and what we'll see, so none of this is really at all useful for trying to do anything to really get your hands on what's going on. You can't actually compute these things. Starting next time, we'll start talking about the harmonic oscillator, and then the harmonic oscillator version of this representation. When you get to that, then you can actually, anyway, then you can see exactly more. You can see this happening, and you can see why it ends up having to be a plus or minus. Okay, so I think I wanted to stop there. So this.
But instead of plus and minus, is it possible to multiply this with any kind of complex number with length 1?
No. Okay, so this is for yeah. So this is for D finite. Yeah. The theorem is that for SP of 2D for D finite, you can in the theorem. Remember, is that you see. So the problem why this is complicated is if you construct this in some way, you can always put some kind of, you could always attach some phase dependence depending upon K to each of these guys and try and make this function go away. Okay, but the theorem says that for basic topological reasons, you can't completely get rid of this guy. You're always going to be, you can only get rid of him up to a sign. So it's similar to the story in the spin case. But then if D is, if you go to D infinite and there is a context where you can make sense of this whole story again, and in that context, then this is no longer true, and this guy can be an arbitrary phase. Okay, so that's, anyway, it may or may not have been a good idea to go to this, but this was just a bunch of abstract nonsense. I mean, this kind of uses this very abstract point of view about what we're doing with quantization, and the interesting things you get out are some very subtle information about quantization, which in the case that we're looking at is just this weird sign problem, and in general, when you get to quantum field theory problems, it shows up actually as a more serious problem, something more than a sign, and it's called the probability anomaly. Okay. Okay, so that's that for that, and so I think let me stop with all this. I think I've gotten far too far into some kind of very abstract stuff, which is very hard to, because it's very hard to actually, just to say anything about these use of K's, to actually construct them. But let me go move on to the next thing I want to do, which is to, like, as often in this course, go back from some abstraction to something much more concrete. And I want to tell you about a much more concrete problem. Okay, and so we'll start by saying something that's a bit general, which is, so the first thing to do I want to talk about is what are called central potentials. Okay, and so this is just that the remember, so here. So this is all going to be in 3 dimensions. This is all in the physical dimension, and so h is then 1/2m, and then p1. Well, let's write it classically: p1 squared plus p2 squared plus p3 squared. And then now if you so this is a free particle. Now if you if you wanted to make this a more interesting problem, you want to couple a free particle to some kind of background, which is going to provide a force on it. So you pick a potential, some function v of q1, q2, and q3, and so this is kind of the kind of general classical mechanical system, a simple one that you normally talk about, which is a particle, and then it's got some kind of potential, which is and you have to understand its motion in this potential. Okay, but what you want to do? Okay, and then quantization is when you quantize, you're just going to turn these things into operators, and there's no operator ordering problem here. So the Hamiltonian operator is 1/2m, p1 squared plus p squared, and then whatever your function was of q1's, but at least for polynomial functions, there's really no problem because these q's all commute, so there's no operator ordering problem. So you can just plug in the operators. Okay, so this is your general problem. But now, and what if this is 0? What makes everything really simple is that your translation invariant. So p's are actually conserved, and you can exactly solve things. Here, once you have a non-trivial v, you're no longer translation invariant, so you can't exactly solve anything. But what you can do though is okay. So the central, but if v is
well, I'm a little bit confused. So the two, how are these two bits related? Do you mean by this that if Q1 and the Q1 are related, Q2 and Q2 are related, Q3 and Q3 are related, then these two bits are the same? Do you mean
which one? I mean, this is this is the classical theory with plus all brackets. And so, but I'm saying that you just use the Schrodinger representation and you construct this operator, right?
But I mean, in first line, the v is defined for little q, but in the second line, v is defined for large q. Then how are these two v?
I'm just saying. Let's just. I'm assuming for simplicity that this is some kind of polynomial function, or I guess yeah. Okay, I have to be more careful. Okay, so you have to. The point is just whatever your sorry. Yeah, I should be more careful because I'm not going to just use polynomials, right? Yeah. So so I have to be a bit more careful, but it's true. So, but what you do is just whatever your expression is for the yeah, okay, yes. Well, anyway, so whatever your expression is for these Q's, when you go to the quantum theory, you just use the same. You use the same expression. You just have to make sense of the same expression for the big Q operators. Okay, actually, maybe a better thing to do is just to say that, okay, this is true for an arbitrary representation. I was trying to avoid using a particular representation, like I could be in momentum space, and so I could be looking at functions of p's. But if I go in let's assume always that I'm using a position space representation. In the position space representation, then Q1, these are really the same thing, because Q1 is just multiplication by Q1. Whatever. Okay. Yeah, it's true. I was trying to think about trying to say this in a representation independent way, but it's true. If you want to work with yeah, if your function of Q is not just a polynomial, then you have to worry about what these operators are going to be. And so let's just, if we stick to this representation, then there's no problem. Okay, so now let's see. So if this function is rotationally invariant, okay, so this potential is some potential depending upon where you are in space. But if it's really if it doesn't actually depend really where you are in space, or the only way it depends on where you are in space is by the distance from the distance from the origin, then you call it a central potential. So if it's invariant under rotations about some point, invariant, then V is really a function of R, which is R squared, which is Q1 squared plus Q2 squared plus Q3 squared, or and then the only operator that actually appears here is then going to be okay. Let me just say that, and then it's the same. Then it's the same thing here. It only, in terms of these operators, it only depends upon the sum of their squares, and the sum of their squares acts by the radius squared, by the distance squared to the origin. So Q1 squared plus Q2 squared plus Q3 squared acts by multiplication by R squared, where R squared is the distance from where you are to the origin. Okay, so now what we want to do, so now let's so if we're in this position space representation, then H is and for now I'm going to put back H bars just so I can get energies with the right units. So H bar squared over 2m R times the Laplacian, which is times the sum of the squares and the sum of the squares of the derivatives. And then this guy in the position space representation, this guy is just going to act is the multiplication operator by V of R. So there's some, whatever the function of R is. So it's just going to depend on the sum of the squares of Q1, Q2, and Q3, and by some function. And this operator acts by multiplication by this function, if you like, times an identity operator. Okay, so what you can do then is you can write this out. Okay, so what you want to do is you want to find. So the problem in quantum mechanics always is, if you want to solve the Schrodinger equation, what the Schrodinger equation tells you that things are going to change. I dt of your psi is going to be given by this operator applied to your wave function. So if you want to solve Schrodinger's equation, what you want to do is you want to diagonalize H, and so you want to find the Eigenfunctions and eigenvalues of H. And so what you want to do is you want to find want to solve. Actually, maybe sorry. Let me go before I get to this. Okay, so that's going to be the next step. The next step is we're gonna, what we really like to do is we'd like to actually. This is a second order differential operator. We want to find its eigenfunctions and eigenvalues, and those are going to be the energies. But what we want to do is we want to somehow use the fact that okay, so what I want to do is I want to use the fact that we're rotationally invariant. So I would use the fact that we're rotationally invariant here to say this is just a function of r. But now I want to use the fact that we're rotationally invariant to re-express this guy in a simpler way. And so what you want to do is go to spherical coordinates. And then rewrite the Laplacian in spherical coordinates. And what you find is that delta is it's got this. It's a second order in r, but it's got a plus 2 over r dvr. But then the angular dependence has a special form. As it turns out, so this is where I'm kind of avoiding. So let me just write down the answer, and you have to go and you have to work out the calculation. But it's 1 over r squared times times an operator, which that L. So this depends on theta phi dv theta dv phi. But the point is, and this is really, well, anyway, if you go back to what we did in chapter 8, where we looked at the expression for the Casimir operator for the action of SO3 on functions in R3, well, we found it was a second order differential operator in terms that you could write in terms of these guys. And if you check, it's the same. It's the same one that appears in the expression for the for the Laplacian. That gives you the angular dependence of the Laplacian. So the basic fact is that you can take all the information about the angular dependence of the Laplacian operator, and it shows it all comes down to this operator L squared, but it's one you already saw. So what you can do is do this. So the way to solve this problem is to use the fact that we know if you break up H into subspaces where L squared acts by spin in L, acts by and that's always going to be L times L plus 1. So spin L is equal to 0, 1, 2, 3, etc. So what you do is we use the fact that everything that we did with the representation theory of SO3, which said that any kind of representation of SO3 is going to break up into parts that are representation that are invariant under rotations that behave like spin 1 under the representation or spin 2 or whatever. And you can figure out what those are by seeing what the eigenvalue of the Laplacian was. And it's always going to be L, an integer times an integer plus 1. Okay, so this is the basic first base, the main basic use of representation theory in this problem. It's to use the representation theory of SO3 to break up. So in other words, we break up H into H, if you like, H0 plus H1 plus HL. So we break the state space, the possible states, up into pieces which behave as sums of irreducible spin 1 representations or sums of irreducible spin L representations, or more explicitly, just diagonalize this operator, and these are the eigenvalues, and then these are the eigenspaces. Okay. And then what you do is then solve and try to solve to try to find the energy. Oh, okay. And then one other crucial thing is that, remember that the Hamiltonian. Yes. So let's say this here is that the Hamiltonian and L squared commute. Okay. And this is by rotation and variance. So if our problem wasn't rotationally invariant, then the Hamiltonian could move you between these different subspaces of different L. But if the Hamiltonian is actually rotationally invariant, then you can show that this is anyway. Then this is basically because, if you go back to Poisson brackets, H Li is equal to 0. Okay. So you can check that rotational invariance means that the Poisson bracket of the generator of a rotation around the ith axis, acting on the Hamiltonian, gives you 0, because this guy doesn't depend upon rotations around the I-axis. So if you you have this for all i's, and then this implies that you have it also for the sum of the squares, and you get and you get this. Okay, so then so now you know that the Hamiltonian operator is going to since it commutes with this guy, it's not going to change the eigenvalues of this guy when it acts. So it's going to take the HL subspace to the HL subspace, whatever. So you've broken up your problem of diagonalizing the Hamiltonian into a problem of diagonalizing it on each of these subspaces, H and L. Okay, and then then what you do is that try to find the energy eigenvalues in H sub L. So for fixed L. And so then what you end up doing is saying that H is so H is minus, what is it, H bar over 2m, and then this guy minus, and then but now we know that we know that when we're in the subspace, we know how L squared is going to act. It's going to act by L times L plus 1 over R squared. And then we just have to have V. So what we want to do, so our kind of three-dimensional partial, our three-dimensional partial differential operator in 3 dimensions, that problem, if you restrict to the spin L, to the angular momentum L subspace, it becomes a signal variable problem. If you like, all of these guys all become now. Well, anyway, so everything just depends upon the R dependence, And so what you're looking at for is the eigenfunctions. So what you want to do is find eigenvalues, or the eigenfunctions. Are going to be, so what's going to happen is that psi of G vector, if you like, it's going to have so it's going to be no, yeah, actually sorry, I want to do well, so what the eigenfunctions are going to be is there are going to be some functions which I wrote as GL, so the energy, which I'll call GL with a certain energy, which and this function only depends upon R, but then the radial functions, the radial, the dependence on the angles is just going to be given by the dependence on the angles of the functions in the spin-L representation, and these are just the spherical harmonics that you've already seen. So these are these YL, LM data, and M is an element of minus L up to L plus minus L plus 1 up to L. Okay, so there's 2L of these guys, right? Yeah, two. No, sorry, it's minus L. That's what there's L plus 1 of them, right? Now how do I? M, yeah. Anyway, the M's are just these guys. Okay, so in terms of the the eigenfunctions of this operator, we've broken the problem up into the angular dependence, which is just given by we've solved from what we know in representation theory, just by looking at the eigenfunctions of this L squared operator, which are for fixed L, there's M of them with the same eigenvalue, which are given by the spherical harmonics. And so we can get, so our energy eigenfunctions look like this, but then there's going to be, we still have to find this function, and we have to find out what it's and it's going to be given. So let me write this down then. So we have to find out, and these guys are the eigenfunctions for this operator as a function of R. So we want to find. So we reduce the problem is to okay, sorry, that's some, yeah, okay. Anyway, so this is the general problem. But let me now what I want to do is I want to take, let's specialize this now. So in general, if you try and do this, so what you're doing is you're oh, yeah. So let's just say this. So you want to solve H, G, L, E, of R is E, G, L, E of R. Okay. So you find E, and then G, L, E. So the basic kind of problem of kind of partial of differential equations you get, and you often spend a lot of time in the quantum mechanics class taught from this point of view of just studying these differential equations, is you get a second order differential equation in R, which can be kind of arbitrarily complicated, tricky to solve depending upon what V of R is. And so, but you know, yeah, but you can numerically or by power series methods or by some method for given V of R, you can try and figure out what the energy eigenfunctions are going to be, energy eigenvalues are going to be, what these eigenfunctions are going to be. That's kind of a well-known problem in differential equations. What we're going to do, but in general, that's very hard. So there are certain cases though where you can actually explicitly solve this. You can explicitly compute exactly what the eigenvalues E are going to be, and exactly what the eigenfunctions are going to be. And so so one case is what we're going to do next time. We're going to talk is the harmonic oscillator, and that's if you take V of R just to be a quadratic in R. But the case we're going to be interested in here is today we're going to look at the Coulomb potential. Also, so V of R is equal to it's minus, it's negative definite minus E squared over R. Okay. So what this is you know, physically this kind of looks something like this. So that this is something that you can get a. So this is V R. What this is saying is that, you know, the oh sorry, I guess this is a bad. Okay. So this is saying that the Coulomb potential is something that as you go off to infinity, it goes to zero. It falls off as 1 over R, but it's actually negative, and it actually goes it goes down to minus infinity as you get to R is equal to 0. So there's something fairly singular happening in R is equal to 0 that you have to worry about. But if you were and if you're doing classical mechanics, then what you do is you know, I mean, this is exactly the problem of you know, you get the same thing for the gravitational potential. If you've got a small mass moving in the gravitational potential of a large point mass, you're gonna have the same problem, and you have similar things about solving that. And you also you find that classically you can exactly solve the problem and exactly find the orbits for that case. And it turns out that quantum mechanically you can also exactly solve the problem in this case. And we'll see what the solution is. Okay, so we want to okay, so let me rewrite this. And so I've gone through, again, this calculation is the same thing you'll find everywhere, is we want to solve. So I'm going to use, anyway, let me just use a little slight reorganization of the derivatives, and you show that this equation becomes this one. So what you want to do is solve. Well, you solve the eigenfunction problem of minus h squared r squared over 2m, and what was it? It's d squared dr squared minus L times L plus 1 over R squared, then minus E squared over R. And this applied to R.
But where's the 2 over R dr?
The what?
No, I mean the 2 over R dr term.
Oh, yes, sorry. I was trying to avoid something in the notes. So I'm using the fact. I'm using anyway. I didn't want to. I'm skipping a step. I'm using ddr squared RF is equal to. Anyway,
Oh.
Yeah. So if you you use the product rule for this, and then it shows that you could recombine 2 terms into this, as long as, so the trick is don't look for the function, but look for the function times r. Okay. And then you get that this guy, that this is e times r g. Well, so this is a function. It depends upon L. It depends upon E. And then L. And it's a function of R. Okay. So anyway, so this it comes down to this first order, this differential equation in one variable. It's a second order equation. Okay. Now, what you can do, so the standard thing that you do in a in the physics course, and what's maybe in some sense the most sensible thing to do is to just use the kind of techniques that we teach in our ODE classes, and use like a series expansion technique to try to find these, and you then end up finding out that the what are they? Did I actually write these things down? Yeah. Okay. Yeah. Anyway, let me just so I'll just state the answer, and you find. Okay, and one thing to. And then the other thing, the thing that you learned from representation theory was that for each one of these, you could, you had an actual, you actually had your actual eigenfunctions also had these spherical harmonic things in them. So they had multiplicity. What is it? Anyway, so you had multiplicity L. Now I'm getting confused. Is it multiplicity L or 2L? Anyway, so each one of these guys is then going to correspond. You then have to multiply it by the spherical harmonics in order to actually get the real eigenfunctions. And you've got you have all these possible choices of m. It'll give you the same. Anyway, it'll give you the same eigenvalue for the Schrodinger equation, the same eigenfunction for the same eigenvalue for the Schrodinger equation. Okay, so what you do if you go through this, and again, so this is where I'm kind of stopping and not working out the details, and I think essentially any quantum mechanics book will give you the detailed analysis of this equation. But what you're finding, okay, what you find is for E is greater than 0. Okay, so for E is greater than 0, what you find is you find things like your plane wave solutions. You find a continuum of solutions, and people don't normally in this kind of class actually try and write those down, but they're basically what's happening is that if the energy is high enough, the solutions are just kind of plane waves that come in and scatter off this thing. Okay, so your answers are kind of, somewhat deformed versions of plane waves that scatter. And so for U equals 0, you get scattering plane waves. And these solutions, like the plane wave solutions, they're not normalizable. They're they're not in L2. They kind of go off to infinity. Well, what happens is that for E is less than 0. So if you look for negative, so if you look for positive eigenvalues, that's what you find. If you look for negative, you find a continuum of these things. If you look for negative eigenvalues, you find that you get solutions for, you get L2, 3. So you get normalizable solutions, and so these are localizable solutions. These are going to be solutions that were that most of the most of the norm of the solution is near r is equal to 0. So you get L, 2 of our solutions for n, let's see, for n greater than L plus 1, and greater than or equal to an integer, and then with E, sorry, so okay. Let me just say it with N. Okay, so N equal to 0. Okay, so for each n, and then E sub n is equal to minus, so then you get all these constants appear this way, 2 h bar squared n squared. Okay, and then so what happens? So n is an integer, and it's so for each n, and you get solutions. Okay, so if you choose n and look at what the possible look at what the possible L's are. Have I got this right? It's get solutions. L is equal to 0, 1, 2, up to n minus 1. Okay. So you actually get for anyway. So you get these eigenvalues that look like this, and for each integer and the corresponding L's. If you fix n, you get solutions with L is equal to 0, 1, 2, 3 up to n minus 1. Okay. So anyway, but I'm not here. I'm just kind of reading off an answer to you. I'm not telling you the details of how you get it. Okay, and then let me so I can get on to the next thing. Let me not say more about this. So in my notes or in any textbook, you can go and look at the for each n, you can find what the GLNs look like, and anyway you can write these things out. They're in terms of an exponential of r and some polynomials called Laguerre polynomials, but that it's just that's a standard computation. Okay, but instead of just kind of telling you this answer, what I want to do is I want to give a way of finding finding this formula. I want to try and the remaining time give you a quick derivation of this formula, which uses the fact that there's an extra symmetry of this problem. So normally, I mean, if you just write down some equation like this, you expect these numbers to be some fairly just some random real numbers which you have to compute. The fact that these actually have a simple formula for them and you can exactly solve for them indicates that there's some extra structure going on here. So let me quickly tell you what that is. But this is kind of, if you want to see more of this, and you really should kind of look at the notes or look at a physics textbook, because this is worked out in gory detail there. Now let's see what's the slick representation theory trick for finding that formula. Well, here and again, I don't have that much time, so what we're going to do, so it's going to go a little bit fast, but this is the maybe I'll say more about it next time. But the idea here is that in the case for the Coulomb potential, has an additional has, well, So3 symmetry. So there's the So3 symmetry you know about from rotations. Plus another non-obvious. So the trick is that there's another SO3 floating around, which acts on this whole thing and preserves the Hamiltonian, and it's not so obviously seen. I mean, it is related to kind of how you solve the kind of Kepler problem in classical mechanics. But the way I wanted to explain this here. So let's look at this. What I'm going to do is it's easiest to see the symmetry classically, as in terms of in terms of phase space, and then you finding the function that generates. So classically, let's find the function on phase space. That generates this. Okay. So we're going to try to find the n-log for this new SO3 of the angular momentum operators. We're going to try to find the moment map for this new SO3 function. And so what you do is you have you have h is 1 over 2m, and then p vector squared minus e squared over r. Okay. So this is your function on phase space for the Hamiltonian function. It's non-polynomial. You're dividing by the e squared divided by the square root of the sum of the squares of the q's. So it's a function on this is a function on phase space. And what you find is that if w vector is equal to 1 over m, and then you take L vector, you take the angular momentum functions, take their cross product with the momentum, and then add e squared and q vector, and then the vector pointing in the radial direction. Okay, you find this really is this is not obvious. There's some ugly computations you have to do to see that this actually works. But if you do the ugly, and I won't actually work those out, you can. I think those may be a problem thing. But if you do those, you find that the components of this function. So the j. So this is a vector for each. It's 3 different functions w sub j, and so each wj is a function of q's and p's given by this, and you find that its Poisson bracket with this function is 0. So it's the same kind of computation that you would do with them if you show that the Lj, that when H is rotationally invariant, the Lj's Poisson commute with it. Okay. And so what we're ultimately going to do is we're going to use the fact that not only can you take these L sub j's and make them big L sub j's, and there are operators that commute with a Hamiltonian operator, and you can diagonalize them. We're going to do the same thing with these guys. But it all is based upon this is one of the main facts, and it's not meant to be obvious. And so it's specifically true. To make this work out, you have to have the Coulomb. It has to be the Coulomb potential. If you put a different potential here, it's not going to be true. So it's a special extra symmetry of the Coulomb potential. Okay, but then the other things you find out that, and easier to see, is that Lj, if you take the Poisson brackets like these guys, what you find is you find this epsilon jk k l w l. So you have this totally antisymmetric sum of the WLs, and this is exactly what you would expect if this guy behaves like a vector under rotations. So you basically identified this is called the lens vector. And so you basically found a kind of new vector which is a lot like the angular momentum vector, and but its its commutation relations are what you would expect, are exactly the same ones that you infinitesimally get when if you do an infinitesimal rotation on a 3 vector. This is what happens. You should have, and so under rotations it behaves like a 3 vector. So it behaves properly under rotations. But then here's the trickiest one, that is what happens if you take the Poisson brackets of the W's with each other, with themselves. Let's do this. So you have to do this computation, and you find out that the Wj, Wk, if you take the Poisson bracket, you get a so you get epsilon jk l, and then this is L sub L. sorry, these two L. This is the L for angular momentum. This is the indexing L. Sorry about that. And then, but then you've got minus 2h over m. Okay. So in general, this is actually a really kind of complicated mess. So in general, this is saying that if we take the Poisson bracket of these guys, we get some of the angular momentum stuff, but then we also get minus 2 over m times this kind of complicated function here. So this Poisson bracket is a mess, but what we can do is we can fix. Okay, so what our idea is going to be is we're going to quantize and then look at fixed energy eigenfunctions. So H can be replaced by E. Okay. So what we're doing is we're looking at this problem and trying to kind of fix what happens if you're working at a fixed energy. So you're just looking at a subspace of fixed energy classically, or quantum mechanically you're looking at energy eigenfunctions of a fixed energy. Because the idea is that this is then just going to become a constant if you have a fixed energy, and depending upon, then you can then reorganize these Poisson brackets and use representation theory to solve your problem. But what happens depends upon the sign of this guy. So let me okay, let's see, and there's
sorry.
Yeah.
After quantization, then the Poisson bracket will become just commutative, right?
Just yeah. So okay. So what you have to do? Let's do it. So what you have to do is you have to find. So you have to quantize. So you want to find, and so you have. There's the same problem we had before. That you in principle you have operator ordering problems to worry about. That you have to worry about. Sorry, I erased the formula for what these guys are. In principle, these guys are just a formula of P's and Q's. But so in principle, you can just plug the P and Q operators in there. But you've got two problems. One is you've got a problem of you have to worry about whether that there are different possible choices of operator ordering, and something subtle and funny is going on in this problem, which I commented a little bit about. is what you find is that you have this no-go theorem. So this guy is actually going to end up being a cubic function in terms of the q's and p's, but anyway, he's a higher order function in terms of q's and p's, and you have this theorem, this no-go theorem, that said that you can't find, there are no such interesting subalgebras, finite dimensional subalgebras that are bigger than the one with the quadratics. That was your no-go theorem. But here you beat the no-go theorem by not making this work on all of phase space, but by doing something that only works on certain parts of phase space, on the parts where the phase space has positive energy or parts of negative energy. So there's a tricky way in which this construction gets around the no-go theorem, and it comes about because you're not uniformly doing something over all the phase space. You're doing different things depending upon whether you're in positive energy, zero energy, or negative energy. And so let me just say what you do and what the answer is. So what works, and in the sense of Dirac, in the sense of turning these Poisson brackets into the right commutation relations, is that is to take W vector to be what, 1/2m. So you do this. So this deals with an operator ordering problem there, and then you have E squared, and then your Q vector, and then here you have that. This is your R squared, but so in the position wave function thing, this is just the R 1/r squared. Oh, sorry, Q 1/r. So what works is that, and then you find that the WJ H the Poisson brackets turn into commutators with the same properties, that you have LJ WK is IH bar epsilon JKL WL, and then what you have is that these guys WJ WK is equal to IH bar epsilon JKL L, and then you have a minus 2/m. So you get you use one way of saying it is that you use your Poisson brackets to just as inspiration to construct this operator, which is going to have these commutation relations. Okay. And then what you also have, and you can also check that this is true, that this guy is 0. You can also check that you have this identity, and then okay, so now what we've got. Okay, let's see this. Okay, I better try to finish this. Okay. So now we've actually got three kind of Casimirs here. We've got the Casimirs for this SO3, the Casimirs for this SO3, and we've got H, I guess. So we got H, and then these Casimirs for the two SO3s. And so what you want to do is you want to take what you do is you find the W squared, so that you get Casimir relations. W squared is equal to e to the 4th times the identity operator plus 2/m H times L squared plus H bar squared times identity. Okay. And so what we're going to do is we're going to use this relation. We're going to use this relation to solve to see what the energy eigenvalues are going to be. We're going to re-express the energy eigenvalues in terms of the L's, and then the possible anyway, the possible values of W squared. That's the trick. Okay, so I'm running out of time. I think I have to tell you then quickly what the there's the basic tricks that you use to get this calculation to work out. Let's do that. So the tricks. One is to pick E, to pick a possible energy value E, and then define. Then you change the normalization and you define. Then to define K vector, which is square root of minus m over 2e w vector. Okay. So instead of working with these guys, we're going to work with these guys, and this is going to get rid of the problem we had on the right side of that complicated. The W's had their Poisson bracket was some complicated thing in terms of the energy. Well, if you renormalize it this way, this guy's going to behave in a much simpler way. And then, so this relation then becomes 2h k squared, but the Casimir for this guy plus h bar squared 1 is equal to minus m to the fourth. Okay. And then what you want to do is that 3. So you assume for e. So we're interested in the case of e less than 0, these bound states. And then what you can do is define 0, 5. So define m as a half L plus k, n vector as a half L minus k. Okay. And then so your problem was that you had if you took Poisson brackets of L and K, they weren't 0. The L and K didn't Poisson commute. But if you do this, then M and K will Poisson commute, and you get two So3 Lie algebras. You know, the M sub I and the N sub I. Okay. So the point is that if you look at the Poisson bracket relations for these guys or the commutation relations for these guys, they're just the So3 commutation relations. Same thing for these guys. But doing this trick splits the L and K so that they don't interfere with each other. They're two. So you have two independent So3s. And then you have to use the fact that L dot K vector equals 0, that implies then that if you take the Casimir for this guy and the Casimir for this guy, you're going to get L squared plus K squared plus these cross terms. Well, the cross term actually has to act as 0. So this implies that m squared is equal to n squared. That the Casimir, so you have two SO3s, and they each have a Casimir operator, but you have a because of the you have a relation which is built into this, which says that that these two Casimir operators are going to act on states with the same. They're going to have the same value. And then what you do is you just solve this, and then you plug in the possible values of either one of these Casimir operators into here. You rewrite this guy in terms of that m and m squared and n squared, and you plug in the possible values, and then you get your answer. You get that E is so. And anyway. Anyway, you then end up with E is equal to minus m e to the fourth over 2h bar squared, 2 mu plus 1 squared, and then where mu is half integral 1/2 1 3/2, etc. Okay, so I won't. Anyway, I skipped a whole bunch of details here, but I did actually write out in the in this chapter of the book. So this story here that I'm telling you is not in the last story. The story about this extra SO3 and the lens vector and how to quantize it and how to use and how to split things up into an extra SO3 and then use the properties of the Casimirs of the two SO3s to find a formula for the energy. That's in a few physics books, but not in most of them. But the details are worked out in the notes. And I think I've gone on too long about that. But let me stop there. So this method, I don't know that. Anyway, this at least gives you the energy eigenvalues by a fairly slick method. Let me then maybe stop here. So, are there any questions about this at this point? Or, of course, you can come back to a while. We can talk at more length. But is there anything in particular about this calculation? Okay. And yeah.
Just making sure. So is mu like somehow the eigenvalue of one of the n operator, or?
Yeah. Yeah, so you're using the fact that mu is just defined to be the so m squared has eigenvalues mu times mu plus 1. It's the one for m, but they have to be the same anyway. And then there's also, normally before I wasn't keeping track of h bars, but if you keep track of h bars, there's h bar squared, and then this is a scalar times the identity operator as well. So that's true. And there's a slightly, you have to think a bit also to figure out, are you actually talking about, these are all the algebra relations, and in the case of should you try and exponentiate, and are you going to get are you going to get the half integral spin representations, and or are you not? And you have to think about that a little bit. But it turns out that you actually do. This is really a Lie algebra calculation, so you just get the Lie algebra representations, which include the spin ones, and not only the spin 1/2 ones, not only the integral spin ones. Okay. Anything else? Okay, yeah.
In the book, you mentioned that this is an SO4 symmetry, and so I guess that's because the SO3 Lie algebra is the same as the SO2 Lie algebra.
Yeah. So the basic. So why I'm saying SO4 is just this fact that we showed at some point that remember, so we showed these facts. So remember that so Lie SO3 is the Lie algebra of SO2. They're all the same thing, and it's just these things with these epsilon jk things. But then if you acted with I showed at some point that SO4 has a double cover spin 4, which is really which is SU2 cross SU2. Okay, and so or if you like, okay, and so what am I? And then SO4, which is so SO4 is really this guy. Is this right? Spin 4. Now I'm confused myself. But is there a double? Yeah. Anyway, so SO4 is then spin 4 mod Yeah. Okay. Yeah. It's this guy. But remember, there's a Z2. So this guy is a double cover of this guy. So, but at the levels of Lie algebras, you find that the Lie algebra of SO4 so is the same as the Lie algebra of spin 4. I could have said either one, and it just splits into two of these guys. It's the Lie algebra of this guy plus the Lie algebra of this guy. So it's Lie SO3 plus the SO3. So it's just two. So when I'm just using the fact that we in this problem we actually have two independent SO3 Lie algebras. These are the ones given by the m's and the n's. Okay, and so I took this L plus or minus k to split these things. But the interesting thing about this problem is that there isn't there's no obvious SO4 group here. It's not like the so you find these two you find these two Lie algebras in the problem, and they're symmetries of the Hamiltonian. They give you generators that Poisson commute with a Hamiltonian, but there isn't any there's no kind of four-dimensional object that's getting rotated somewhere that would explain this. So the explanation is a bit mysterious about where these things come from. But but saying that you know that this has an SO4 symmetry is really just saying that it has a pair of SO3 symmetries. That's really all that's being said here.
So for the equation, the SO4, why do we just model one copy of Z2 instead of two copies of Z2, one for each SO2?
Well, this is for well, the spin group is always the double cover of the SO group. Okay.
Okay, so that's coming from that.
Yeah, and the way to remember it here is that a way to think about rotations in four-dimensional space is to think about them as about take a quaternion and then left multiply by one unit quaternion and right multiply by the other by another quaternion here. Okay, and so you can rotate 4 dimensions if you think about these as being elements of R4 because they're quaternions. You can rotate in 4 dimensions by and these guys are elements. They're unit length, so they're elements of SP1 or SU2. Okay, so a pair of quaternions gives you a rotation. So, but the problem is that if you take there's a little bit of a double counting here because if you take the quaternion -1 here, if you multiply this one by -1 and this one by -1, you'll get the same rotation. So that's where this comes from. Okay. Okay.
Got it. Okay.
So rotations in 4 dimensions really are given by pairs of unit quaternions, and they're not SO3s. These are really quaternions are really SU2s, and so unit quaternions and there's a this is just the -1 problem in that. Okay. Anything else or? Okay. If not, so then I'll stop this. But do come back in a few minutes if there's anything else you'd like to talk about besides this. And apologies for some of this today went by way too fast. Some of it went by too fast because it's kind of a detailed thing about ODEs that's in any physics textbook I didn't want to spend time on. But some of it, the last stuff is kind of tricky, and apologies for going through that too fast. But at least I hope given in some detail in the notes. Okay, bye for now.
Thank you.